The next thing from chapter 19 that we have to talk about is something called the Michael addition. Michael addition. The Michael addition. And what that involves is something called an alpha-beta unsaturated ketone. That's a fancy word, but all it means is a ketone that has a double bond between its alpha and beta positions. Now, up until this point, we've had everything going out and attacking carbonyls, right? These alpha-beta unsaturated ketones have their own special rule. Let's draw a resonance structure for a second. I have O, double bond, that. Well, we know that oxygen likes to pull the electrons of its double bond up towards itself, and you get O minus carbon positive, and everything else the same. But now consider the fact that this positive can also resonate with that double bond. And that's what makes these react a little differently. If this double bond resonates down towards the positive, now you're left with an O minus, an enolate, and now carbon positive on that beta position. And so when we have a nucleophile come in that can react with either the carbonyl or this carbon over here, there's a good possibility it's going to go for that positive carbon. And now there are a couple of reactants that are specific to the carbonyl and others that are specific to the C double bond C, and we have to figure out which one's which. So I think it's easier to talk about the ones that we know attack the carbonyl first. And those are your Grignards, so carbons that are attached to MgBr, and carbons that are attached to lithiums, your alkyl lithiums. Both of these reactants, where you have carbons with lithium or carbons with MgBr, always specifically target the carbonyl, the C double bond O. In both cases, all these do is put a negative charge on their carbon that they're attached to. So I basically drew the same thing. For all intents and purposes, MgBr and lithium do the same thing in this course. And that negative charge is going to come in and always preferentially attack the carbonyl. That would swing up, and you're left with an O minus. The carbons that you added, I had 1, 2, so I should have 1, 2, and then the carbons that were originally there. This double bond does not get touched whatsoever, and then usually there's a step 2 H plus source, where that O minus will come in, grab that proton, and end with an OH. So this would be your final product. On the other hand, there are a bunch of things that like to react with the carbonyl, the carbon-carbon double bond instead. In fact, basically, if you don't see this or the MgBr or the lithium, it's most likely going to be reacting with the carbon-carbon double bond. So nucleophiles that like to react with that. The most common ones I've seen are C triple bond N, N3. N3 is a crazy molecule, but you'll learn more about it when you get to the chapter 20 material, I believe. But for your purposes, just know it's a good nucleophile. Oxygens that are negative, so for example, OCH3. Nitrogens that are negative, so like NH2 minus. And one really weird looking thing called the Gilman reagent. The Gilman reagent will look like this, CuLi. So you see lithium, but it has copper in this case. So it's different from just the lithium we were showing before. And then in parentheses, you have some R group. I'm just going to say CH3, close parentheses, 2. Now this looks weird, but it's actually really, really straightforward once you know what it does. In any case, let's work with one of these first. Let's do the C triple bond N, and then we'll worry about the Gilman reagent afterwards. So what happens here? We already saw through resonance that this carbon on the end of the double bond becomes positive. And that makes these negative nucleophiles really want to attack that carbon. Which means any one of these will come in, attack that carbon there. Now this carbon has 2 hydrogens on it, which means it doesn't have room to make another bond unless it resonates over. Which means this double bond will resonate down towards the oxygen, and then the oxygen will resonate up to make room for that, giving you this key intermediate, an enolate, an O minus, because this swung up, a carbon-carbon double bond because these electrons moved here. The carbon that got attacked is this one, and finally, the carbon that got attacked, whatever attacked it is attached to that position. In this case, C triple bond N. So if I number my carbons, I have 1, 2, 3, 4, and 5. And here I have 1, 2, 3, 4, and 5. Now this isn't the end of the reaction because we're left with an enolate. And one thing I want to stress very much so is if at the end of a reaction you are left with either an enol or an enolate, enolate being O- on a carbon-carbon double bond, enol just being an OH on a carbon-carbon double bond, you will always do what's called tautomerization, where this swings back down, forms its C double bond O, and this goes out and grabs a proton from something. So somewhere around here there's an H plus floating around. Sometimes it's, if we have Cn minus, we also have a little HCN floating around. Whatever the source, that O minus will swing down and this will grab that proton and you will be left with double bond O, 2, 3, 4, and then C triple bond N. This is the final product of your Michael addition. Michael additions end with the loss of the alpha beta double bond that you started with, okay? And the reformation of that carbonyl. So the fast way of doing any Michael addition, let's say I had N3 minus here reacting with the same alpha beta unsaturated ketone. Look at your carbons and find your beta position on that double bond. So it's always the end of the double bond. You can redraw the exact same molecule that you're starting with. 1, 2, 3, 4. But now erase the double bond that was between 3 and 4. Leave it a single bond. And on that carbon at the very end, tack on whatever was doing the attack. So this would be the final product of the N minus, or the N3 minus. Okay? And it's basically the same thing here. I just, instead of N3 minus, I have C triple bond N. Okay? Now what does the Gilman reagent look like? Well, I don't want to draw it out because it looks kind of weird and takes up space. But basically, whatever is in the parentheses, you're going to be adding that to the beta position. So you can picture this as if it was CH3 minus, just not a CH3 minus that you get from MGBr or lithium by itself. So what that means is, let's say I have the same alpha beta unsaturated ketone as before, and I'm reacting over the arrow, CuLi parentheses CH2 CH3 close parentheses 2. I'm only adding one of these. Even if there are two, I'm only adding one. And I'm adding that CH2 CH3 to my beta position, the end of that double bond. So just like I did here, redraw what you started with. Now erase that double bond. And that carbon that was on the end of the double bond, stick whatever in the parentheses there. CH2, CH3. So CH2, CH3. I'm adding two carbons. So I have 1, 2, 3, 4, 5, and 6. And here I have 1, 2, 3, 4, 5, and 6. And the mechanism is just like what we were doing before, where one of these carbons comes in, attacks there. Let me change the color. Next there. This swings up. This swings up as well. You're left with this as an intermediate, O minus, enolate, 3 and 4, and then the two carbons you added. Then this tautomerizes back down, grabbing a proton, wherever that proton may come from. Sometimes it's just a step 2H plus, and that results in this as your final product. Okay? So the Gilman looks weird, but it's nothing too crazy or new. There's one other little important bit I want to mention about the Michael addition. And it's not really so much how it reacts, but how do you make its reactant. So we said before that the reactant of a Michael addition is an alpha beta unsaturated ketone, a fancy word for a ketone that in its alpha and beta positions you have a C double bond C. Now, one thing you have to notice is if we're going backwards a bit to the first thing I talked about, or one of the first things I talked about in chapter 19, you have a 1, 2, 3, a carbonyl on 1 and a C double bond C between 2 and 3. So this should stand out to you as the product of an aldol condensation. Because if I used heat going backwards, I would end up putting a C double bond O. I would end up getting an OH back on carbon 1. Or sorry, carbon 3. And then we saw before that the bond that forms in a aldol reaction is the bond between 2 and 3. So going back further a step, I know that the two reactants that came together using OH minus as a base would be the carbonyl with carbon 2, and then plus this going back to a carbonyl, a formaldehyde, right? Because what happens is this OH minus pulls off the proton here, making that carbon negative, and that negative carbon attacks here, swinging that up, making O minus, which then grabs a proton. So the Michael addition reactant can be formed by a reaction involving a ketone or an aldehyde, depending on if this is a methyl or an H, and formaldehyde with heat. Okay? So I could say these two pieces, and then I write OH minus and heat, and that will give me my Michael addition reactant. Okay?